All right, I want to talk about modeling for a minute. And a lot of times we think about modeling in terms of the ways that we visually model things or the way that we model things with computers or regression models or statistics. But really the main part of modeling happens in our minds and in the way that we lay out the relationships that we expect to see between variables. So the important part of modeling actually is a uniquely human thing. It's a creative thing. And it is humans who are inputting models into systems that help us to understand the world around us. And so I want us to think very carefully about how we put these models together. And we're going to talk about three specific types of models that are really common, especially using the sorts of statistical analysis that we'll be using through regression. So the first thing we need to do is remember the relationship between X variables, Y variables, and Z variables. So if you look at this board, here on the top, I have one way of thinking about things, and that is if we're trying to establish a causal relationship, we have a cause variable, our X, and our outcome variable, Y, and we need to remember to control for our Z variables. And you'll notice here that I don't just have one Z, I have many Z variables, Zn, meaning that we have multiple different control variables that we would include. And another way to look at this little equation or to think about this is this next item here, where you can see that Y is a function of our X variable and the Z variables. In other words, the outcome is a result of the cause, and we're controlling for additional variables. So I like to think of this as sort of the base model that we run, and it's a single cause model. In other words, we're really interested in the relationship between X and Y. We want to see if X causes Y, and on the way to doing that, we have to establish correlation between X and Y. And we also need to rule out plausible alternative explanations, which is why we include Z variables. So in a model like this, we would have a single outcome variable, our Y variable, and we'd have a single independent variable that we care about. This is our research variable, or the variable that we're really going to interpret. And then we'll also include other variables, but we're not as interested in the results of these variables. They're just there to rule out other possible plausible explanations for why we might see a correlation between X and Y. So this is a single cause model. The next type of model is similar, but here, instead of just one cause, you'll notice that we have multiple cause variables here. So I like to call this the greatest cause type of model. We still, sorry, gotta get us in the right position here. We still are controlling for Z, a set of Z variables, but now we're interested in more than one potential cause for Y. And a final type of model that we often use regression analysis for is what I call a predictive model. And in this case, we don't actually have a specific variable that we're asking questions about. We're not trying to establish a causal relationship. What we're trying to do is do a really good job of predicting Y. We want to know what's going to be going on with Y in the future, or if we have any particular observation or case, we want to be able to guess what the likelihood is that it's going to yield this Y outcome. So this is all very abstract. We've got like algebra kind of stuff going on here. We've got letters and ends and squiggly things. Let's put some examples to it to see if that helps a little bit. So one example of a single cause type of question is if we're trying to predict the outcome of coronavirus infection for an individual. And so what we would do is we would gather a lot of individuals together, and for each of them we'd measure a bunch of variables, and one of those variables would be, were they infected with coronavirus? And so that is the outcome that we care about. And in this particular question, we're going to have a single cause question. In this particular question, I'm interested in whether or not being a consistent mask wearer is associated with lower coronavirus infection. So in this case, what I'm expecting to see is an inverse relationship. In other words, The more likely someone is to be a consistent mask wearer, the less likely they are to have been infected by coronavirus. So this is my real causal question. And in order to establish whether or not being a consistent mask wearer causes decreases in the likelihood of coronavirus infection, I need to establish that those things correlate. I also need to rule out plausible alternative explanations. So in this model, I'm not just going to see whether consistent mask wearing is associated with coronavirus infection, but I'm going to measure a bunch of other stuff too, and I'm going to include that in the model. So this might include things like age, and it might include prior health conditions. It might include the number of social contacts that a person regularly has. And I might include, let me do this so you can actually see it, whether or not they're a consistent physical distancer. So this is still a single cause model. I'm still only really interested in whether or not being a consistent mask wearer has an impact on coronavirus infection. But in order to establish a causal relationship, remember I need to do 4 things. And among those 4 things are establishing correlation and ruling out plausible alternative explanations. So because of that, I'm going to include all of these control variables in that same model. But when I interpret the model, what I'm really looking at, what I'm going to focus on is whether or not there's a relationship or a correlation between mask wearing and coronavirus infection. So that's the first type of question that we might ask that we model with regression analysis. Single cause, we're only interested in one X variable. So let's move on to the second kind of cause, and I'm actually going to sort of retask the same example. So let's say that in our greatest cause example, we are trying to predict coronavirus infection, but this time we have a slightly different question. We want to know which is more important. In other words, which is most correlated with either becoming or not becoming a person who's infected with coronavirus. Is it more important to be a consistent mask wearer, or is it more important to be a consistent physical distancer? So you'll notice I've switched this to a white sticky note as opposed to our pink that we had before, and we're still going to control for all these other same things. Now, what's interesting is that when you put this model into your regression analysis in your statistical software, this model literally looks exactly the same as the model that we ran before. The computer, the software, the math, none of it cares what color these sticky notes are, okay? This is entirely in your head. But for you, you know that the reason that you've included these variables is you want to know which of these 2 variables has the biggest impact on your outcome. In other words, I'm going to be interpreting and watching for and specifically looking at statistics that tell me about whether being a consistent mask wearer or being a consistent physical distancer is more important or more effective in preventing coronavirus infection. And again, I still need to control for all of these things. The final type of model question that we might have is a predictive model. So in this case, I might have coronavirus infection here, and I'm not going to change the color of all my sticky notes here, but I'm going to use all these same variables. I care about all the same stuff, so I'm going to move these all down here. But this time, the question that I have isn't what's the effect of masks, what's the effect of physical distancing, which of those has the biggest impact. That's no longer my question. What I care about is, given all this information I have about a person, how accurately can I predict whether or not they're going to be infected with coronavirus? In other words, in this kind of model, what I'm really interested in is creating a model that does a good job of predicting this outcome. So rather than interpreting the relationship between any particular variable or set of variables and this outcome, I'm just going to focus on how good of a model it is for predicting this outcome. And then I can apply that predictively when I'm looking at people coming in. Maybe I've got someone coming into a hospital, I can have them do a quick survey, and I can actually assess their level of risk for being someone who's infected with coronavirus because I have created a model that does a good job of doing that. In the software, in the mathematical model, these three models were literally identical. It's going to kick out the same set of statistics. Let me try saying that again. It's going to kick out the same set of statistics. The commands that you're going to put in are exactly the same. The math operating in the background is exactly the same. The human part of this is understanding which kind of question you're asking and why you included the variables in the model. In the first case, for example, you included consistent physical distancing as a control variable. That's why it was there. You didn't want to interpret it, you just wanted to rule it out as a possible alternative explanation. But in the second model, you included that as a variable you actually cared about and you were going to pay attention to and interpret the relationship between that and coronavirus infection. And in the final model, again, you weren't so much interested in interpreting the relationship between any individual variable and the outcome. You just wanted to do a good job of predicting coronavirus infection in general. Okay, so that provides hopefully an example of how we might use these three different question types. Again, the math may be the same, the model may be exactly the same, what you put into the software, the command is going to be exactly the same, but the way you're thinking about it, the kind of questions you're asking really should be shaping what you put into your models and why. So the three main question types are: first, a single cause question. And a single cause question is one in which you are looking at the specific relationship between a potential cause variable and an effect variable or an outcome. The second is a greatest cause question. This is where you might have multiple different policy levers that you can pull, or programs that people can be participating in, or choices that people can make, and you want to know which one of those to invest in or which one has the biggest impact. Because we have limited resources and limited time, and so maybe you're comparing across multiple variables to see which one makes the most splash in terms of altering your outcomes. And then the final type of question is a predictive question. And the question there isn't about the correlation between any particular variable and your outcome, but rather the goal is to create a model that is as predictive, as accurate as possible, so that you can use that predictive model in the world to make decisions. So those are the three question types that we can think about when we're modeling. And hopefully this has been helpful for thinking about the relationship between Y variables, which are outcome variables, X variables, which we're thinking about as the variables of interest or the variables that we're going to focus on and interpret, and Z variables, which we include in models in order to be control variables.